Hi, and welcome to our session where we're going under the hood for Google Cloud's data technologies. I'm Leigha Jarett, and I'm a developer advocate here at Google Cloud, and I focus on data analytics. But today I'm also joined by my colleague, Jarett, who focuses on operational databases. Today, we're going to be talking about two technologies. First, Spanner on the operational databases side of things on the left-hand side of our screen. And then we're also going to focus on BigQuery, our data warehouse for analytical processing. And these are just a few of the pieces in the broader Google Cloud data ecosystem. Integrations between both of these products and other products that support data fabric, artificial intelligence, and business intelligence all go into making it simple for data practitioners and business users to power data-driven innovation using Google Cloud. So the story of both Spanner and BigQuery starts with the evolution of the separation of storage and compute. Historically, database systems have been architected with tightly coupled storage and compute. So there's a dependence on locally attached storage because attaching storage to a network would result in higher latency. But more recently, these constraints have been lifted, largely due to faster networks, which we're going to talk about momentarily. So now with architecture like BigQuery and Spanner, we have a separation of storage and compute. And this allows us to seamlessly scale to meet your high throughput data needs. New compute nodes can easily be added to handle large workloads, and we don't need to rebalance the data and ensure that a local replica is stored on new nodes. So let's take a closer look at how our distributed storage system, Colossus, is also faster, reliable, and cost-effective for you. So Colossus is Google's next generation distributed file system. It manages, stores, and provides access to all of your data for both BigQuery and Spanner. Its design enhances storage scalability and improves availability to handle the massive growth in data needs. Colossus introduced a distributed metadata model that delivers a more scalable and highly available system. With all this data stored remotely, if a single node fails, there's no data lost or even made temporarily unavailable. Not to mention, remote storage is dramatically cheaper than local storage. And the proof is in the picture. So not only does Colossus handle your first-party data stored in Google Cloud, but it also stores the information needed to run vital Google systems that are used by so many people all over the world. Like we mentioned earlier, the separation of storage and compute would not be possible without the evolution of networks, which increase the speed at which compute clusters can pull data from storage and reduce latency. Just like Colossus, Google Cloud services like BigQuery and Spanner leverage the same network that powers the underpinnings of Google's systems. And we call this network Jupyter. So Jupyter is made up of an in-house custom network, hardware, and software, and it connects all of the servers in our data centers together, powering our distributed computing and storage systems. So we discussed our file system and the network that connects the storage and compute together. Now, leading all the operations in our data center is Borg, Google's internal cluster management system and the predecessor to Kubernetes. So Borg goes ahead and provisions the needed compute resources to handle workloads for Spanner and BigQuery, running hundreds of thousands of jobs and making computing much more efficient. This allows our data centers to run at a really high utilization. So now let's see how these pieces come together throughout the life of your data. So let's take a look at Cymbal Gaming, our fake gaming company who uses Spanner to support transactional or OLTP workloads. So a new user might log into the Spanner game and enter their information. This data is then sent to Colossus for storage, but it's going to be in Spanner's file format. Next, this data is requested in a query sent through Spanner's compute engine. And finally, the results of the query will be returned in the application to populate the new user's profile when they load the page. So Spanner's storage and compute are both going to be optimized for those transactional workloads. And Jarett is going to talk more about that in a minute. So even though Cymbal is using Spanner for transactional workloads, they also want to perform analytics on this information to understand how users are actually playing their game. But for analytical workloads, they're going to instead use BigQuery. So once the user's data lands in Spanner, they have two options. First, they can replicate the data in BigQuery storage by pushing new rows into the native BigQuery table. This is going to provide optimized storage for analytics. On the other hand, they can use a federated query sent from BigQuery over to Spanner so that they get real-time access to information from their application. Either way, they'll benefit from BigQuery's query engine to perform scalable analyses, including built-in machine learning capabilities that power business intelligence reporting and real decision-making from business users. So now that you understand how BigQuery and Spanner both come together to support your data needs, let's talk about how Spanner is actually optimized for those transactional workloads. So, Jarett, over to you.
Great, thanks, Leigha. Cloud Spanner is Google's fully managed distributed relational database. Spanner provides customers with minimal operational overhead with no downtime for schema changes or even maintenance windows. This allows Spanner to provide an industry-leading 5 nines SLA. Because Spanner is distributed database, it provides seamless replication and scaling across regions in Google Cloud. Spanner processes over 1 billion requests per second at peak, and all of that as a relational database that provides strong external consistency, made possible by the technologies mentioned earlier, Borg, Colossus, and Jupyter. To set up an example, imagine that Cymbal Games has developed a game that will be played by people all around the world. These players must be able to sign up, authenticate, and play the game. Players really don't like to have to redo actions, so this activity has to have traditional consistency guarantees. Another thing players don't like is downtime. If they can't play, they get upset. And it better be fast. So Cymbal Games will need to have the ability to scale up to meet user demand. With availability, consistency, and scalability in mind, let's see how Cloud Spanner can help them achieve their goals. When you create a Spanner node, you get access to Spanner resources in 3 or more zones. Zones are Borg cells. These cells are a collection of Spanner resources that are physically separate from other cells. Spanner resources consist of Spanner servers and Colossus allocations of data storage, as discussed previously. Spanner servers provide the compute capacity for your cluster, and they contain the span process, Paxos, and other Borg tasks to enable Google SREs to manage the environment. The zones can be within a single region, as shown here, or across multiple regions. If you have a regional configuration, you have zones close together that provide the lowest read and write latencies, but you only get an SLA of 4 nines availability. In a multi-regional configuration, your zones are located farther apart, which can increase latencies, but it provides global scalability and an SLA of 5 nines availability. Now, imagine that Cymbal Games has a table of users. The user data is stored on Colossus and encrypted at rest. A copy of this data is in at least 3 zones, and replication of the writes is handled synchronously by Paxos consensus. So their data will survive zone outages and allows for zero downtime maintenances as well. To understand consistency, let's go over typical transaction lifecycles. When a new user signs up, Cymbal Games issues an insert statement to Spanner. Since nodes exist in multiple zones where the insert statement hits depends on which zone is the current Paxos leader. In this example, zone 2 is our leader. A single endpoint is exposed to the client, and Spanner internals handles routing of the query. When the leader receives the write, it acquires locks and generates a true time commit timestamp. Then it sends the write to other nodes in the configuration. These nodes write the mutation to something like a durable transaction log and confirm the write to the leader. After a quorum of nodes approves the write, then the leader tells the nodes to commit the data, it releases the locks and returns the success to the client. All of this usually happens within a few milliseconds. We can't do a session about Spanner without mentioning true time. TrueTime is a highly available internal service backed by a network of atomic and GPS masters. This service can be called to generate a guaranteed monotonically increasing timestamp with microsecond granularity across all nodes. In Spanner, these timestamps are generated for writes. It is precisely because of TrueTime commit timestamps that allows a distributed database like Spanner to ensure strong external consistency. So let's see how they are used for reads. Once a user account has been created, they'd want to be able to log in and start playing. So Cymbal Games needs a consistent read to provide authentication for the user. In this example, the read is going to be executed against Zone 1, since it's closest to the client making the request. But since Zone 2 is a leader, Zone 1 checks in to make sure it has the latest commit data. If the data is the latest, it can be returned to the client. Otherwise, the read waits until the node receives updates. How does the replica know that it has the latest data? With TrueTime commit timestamps. The replica compares its own TrueTime state with the latest commit timestamp to know if it's enough up to date to serve the read. But not all reads of the user need to be strongly consistent. Since user data doesn't change that often, Cymbal Games can choose to issue a time-bound read, otherwise known as a stale read. To do this, they provide the max age that is acceptable for their query, making it time-bound. This allows the Spanner node closest to the client to respond to the query without incurring additional round-trip latency, communicating with the Paxos leader. No matter how fast the Jupyter network is, if you can cut out latency across zones, you should. With availability and consistency covered, Cymbal Games still needs scalability out of Spanner. So let's look at that. As a first step, Cymbal Games gets closer to launch. They can go ahead and increase the number of nodes from pre-prod levels to prod levels simply by updating the cloud console. Next, as the user data grows, Spanner will start to create splits of the data. It does this both by detecting CPU load increases and hotspots, and will split the data into chunks to address these issues. These splits can be hosted on different Spanner servers backed by different Colossus allocations, which helps distribute the load. Data splits and increasing the number of Spanner nodes gives Cymbal Games the ability to scale as much as they need to. But to avoid headaches down the road, they need to be sure to place related data in the same split using interleaving. Imagine user activity data that relates to the user data. By interleaving the user activity table with the user table, Spanner will change the splitting logic to make sure that the data stays together on Colossus. In this way, Spanner scales easily while also keeping performance high by avoiding additional locking required to read or write across multiple splits. Managing this distributed database for transactional workloads is only possible because of technologies like TrueTime, Borg, Colossus, and Jupyter. So now Leigha is going to take it over and talk about analytical workloads.
Great, thanks, Derek. So now that you understand how Spanner is great and optimized for transactional workloads, let's talk about how BigQuery's architecture supports analytical workloads. So let's start by adding the new user data into a native BigQuery user table. As soon as you push data into a native BigQuery table, the data is going to be transformed into a file format called capacitor. Capacitor uses what we call columnar-oriented storage, meaning each column in the table is going to be stored in a different area of the file. So the amount of the columns you query is going to be proportional to the amount of data that's actually scanned. Now, if you think about it, this is optimal for analytics because you're often aggregating just a few columns over lots and lots of different rows. Plus, each column also has independently compressed information. Here we use different types of encodings to optimize storage, which makes it easier for Dremel, our query engine, to quickly find and use the data it needs for your query. Even better, you can choose to cluster or partition your data stored in capacitor so that Dremel can easily eliminate certain files or blocks from the query. Let's look at a quick example of this. So let's say we have our user table and we've decided to partition based on the date that the user was created. we're also clustering or sorting our table based on the game ID. So now when we filter our data based on created date and game ID, Dremel is going to use the file headings in capacitor to reject the entire file or file block if it's not needed for the query. This means that less data is going to be scanned and your query is going to be both cheaper and faster. So in Colossus, your data is stored in capacitor, and it's going to be automatically compressed, encrypted, replicated, and distributed. So 100% of your data is going to be encrypted at rest, just like Jarett mentioned with Spanner. And Colossus is also going to ensure durability using something called erasure encoding, which stores redundant chunks of data on multiple physical disks. So immediately upon writing data to Colossus, BigQuery is going to start this geo-replication process, mirroring all of the data into different data centers around the specified region or multi-region, depending on how you set up your BigQuery dataset. This means that you have backups of your data stored in case of disk failure or data center outages. Okay, so we talked a little bit about BigQuery storage. Now let's talk about compute. So Dremel, BigQuery's query engine, is made up of something called slots. And these are Google's proprietary units of CPU, RAM, and network. And they're used to execute the SQL queries. So BigQuery will automatically calculate how many slots are required by each query, depending on the data size and the complexity of the query itself. You can think of a slot as a worker, and slots are going to be responsible for executing parts of the active query independently and in parallel, and they're going to perform partial aggregations. They'll also read and write data back to storage. So the awesome thing about BigQuery's architecture is that you can actually purchase slots and reserve them for certain workloads in your organization. This means that you can scale your throughput and your runtime as needed. So now let's go a little bit deeper into query execution. First, when you submit a query, BigQuery is going to break it down into different stages, which will be processed by those slots. Intermediary results are going to be written back to what we call the remote memory shuffle. Since data here is usually stored in memory, it's really fast for slots to read and write data from the shuffle. Now, each shuffled row can be consumed by slots as soon as it's created. This makes it possible to execute distributed operations in a parallel pipeline, which means that we can analyze huge amounts of data really fast. And if a worker were to have an issue during query processing, another worker could actually simply pick up from where the previous one left off because they're able to read from the previous shuffle. So this adds an extra layer of resilience to failures within the workers themselves. Okay, so let's say we're running a query to count how many users joined Cymbal games yesterday before feeding them into our ML model. In the first stage of the query, slots will read the columnar files from Colossus in parallel. Each slot processes a columnar file block, filters the data, and then writes the partial aggregations to the shuffle. In the next stage, a slot reads the data from the shuffle and combines those partial aggregations together. Then it's going to write the results back to Colossus so that it can be served as a cache table back to our user. So how do these architectural distinctions of BigQuery actually translate to business value for you? Well, first of all, we talked about how BigQuery's optimized storage and compute allows for super fast queries over huge data volumes, meaning your business will be empowered to make informed decisions without ever missing a beat. Next, we showed how BigQuery helps you save money on data storage and analysis, so you spend less resources answering business-critical questions. We also talked about how BigQuery storage ensures reliability and durability, meaning there's a very low risk of losing information and interrupting business processes. And finally, the ability to purchase and dedicate slots to specific workloads means you can scale throughput and runtime so that you continue to support your business analytics as your data and your use cases grow. And don't just take our word for it. Google Cloud actually has hundreds of BigQuery customers with petabyte scale data warehouses. So thanks, Derek, for walking us through Spanner, and thank you all so much for joining us today to dig into Spanner and BigQuery under the hood. Here, we provided some resources to help you get started using both Spanner and BigQuery, and I've also listed some sessions that are going on at Next related to data analytics and databases. So thanks again for joining us, and we hope you enjoyed this session and that you enjoy the rest of your time spent here at Next.